So this one is an assignment related to fluids and fluid dynamics. We'll start with question 28. Question 28, the raindrop reaches a terminal velocity. Within a few meters of a starting fall. On the axes below, sketch the velocity time graph for the motion of a raindrop. So whenever like a raindrop is there, it has a negligible mass, so its weight is acting downward and upthrust act upward, and the viscous drag will also act upward. So as a result, what will happen? It will reach the terminal velocity instantly. It will not take longer time. It will instantly reach a terminal velocity. Explain why terminal velocity is reached. So what are the points you will refer here for reaching a terminal velocity? Number one, that there is no resultant force acting on this raindrop. So the resultant force is zero. So resultant force is zero, no resultant force is acting on this. And we can say the weight is equals to upthrust plus the viscous drag. Because it is going down, so the weight equals to upthrust plus the viscous drag or the drag force. So as a result, because there is no resultant force acting on it, and this viscous drag depends on the speed. As the speed increases, the viscous drag will also increase. So eventually it will balance with the weight. The sum of, because upthrust won't change. Upthrust depends on density of the fluid, volume of object, and gravity. If these factors remain constant, upthrust is constant. But the moment the raindrop fall, the viscous drag increases with the speed, so which balances with the sum balances with the weight, and there is no resultant force act on the raindrop. As a result, it will move at a constant speed. Suggests why the upthrust acting on a raindrop is considered to be negligible. As you can see, upthrust depends on density of object, density of fluid, volume of object, and gravity. So what we can neglect for a raindrop, the density of a fluid, which is very small, we can neglect that. And same thing, the size, the volume of a raindrop is negligible, very small. So as a result, both factors are very small, so we can neglect the upthrust. After reaching a terminal velocity, a raindrop took 2.6 minutes to fall 1,100 meters. Calculate. So for terminal speed here, speed is distance over time because it is moving at a constant speed. So we can use this equation. No need for equation of the motion as the object is moving at a constant speed. So this will be 1100. Time it should be in seconds, so 2.6 into 60. That will give us the speed at which the raindrop will fall. So 7.05 meter per second. Calculate the radius of a raindrop. You may assume that the Stokes law applied to the raindrop. Viscosity of air and density of air, water is also given. So, and they already mentioned, like, we ignore the upthrust can be ignored here. So if upthrust can be ignored, if we ignore the upthrust, weight is equals to the viscous drag. So weight is acting downward, viscous drag is acting upward. Upthrust is being ignored, negligible. Then weight is mass into gravity. And this is 6 pi eta r and v. What about the mass? The mass is density into volume. So this will be the density, because this is for object, the weight of object. So density of object, volume of object, gravity. This is equals to 6 pi eta r and v. What about the volume of object? The volume of object, because it's a spherical, our assumption, it's only because we apply Stokes law, so means it should be spherical object. So density of object, or because density of a water here as it's a raindrop. What about the volume of object, which will be 4 by 3 pi r cube into gravity is equals to 6 pi eta r and v. Now we simplify this equation. This r will cancel with this, so become r square. Pi will cancel with pi, and this will be 2 and this will be 3. So if we need the radius, like when we simplify this, it will be density of object 2 by 9, or just simplify the numerator, 2 density of object r square g by 3 is equals to 3 eta and v. Now we have all the values. We have the viscosity of air, that's the fluid. We have the terminal velocity. In the previous part, we work out the terminal velocity, which was 7.01 meter per second. The density of the object, density of a water is given. Gravity is constant, so we can just simplify and work out the value for R. So if we ignore, then you can, the formula will change. The shape of the airdrop depends on the velocity. Once at the terminal velocity, the raindrops is flat at the bottom due to a laminar flow around it and remain curved at the top due to a turbulent flow. Add to a diagram to show how the airflow. So there's a laminar flow. How we represent a laminar flow, laminar or streamline flow, like the particles will move uniformly around it. But then at the top, it become a turbulent. So, and remember one thing, the direction of the motion of the object and the fluid will always be opposite. So this is at least you should use 2 lines. When you're drawing a laminar flow, the spacing between the lines should be same. But when it becomes turbulent at the top, you can just make eddies, like it just cross over. So it becomes turbulent at the top. Minimum 2 lines are enough. Maximum it can be any number. Two are enough to show a difference between a laminar and turbulent. Even you can just make it circles here, which means like it just randomly change the direction. The next is Stokes laws can be used to calculate the resistive force acting on an object which moved through a fluid using an equation 6 pi eta RV. Stokes law is only valid if the flow is laminar. What is meant by the term laminar flow? Laminar flow means like there's no abrupt change in direction or speed. So the speed or the direction does not change. Say the conditions for an object to be a laminar flow. What are the conditions for a laminar flow around the object? Like object should move slowly through the fluid. The object must have a smooth surface and the object should be very small. So these are the conditions, like it should have a smooth surface, object is moving slow, and object is very small compared to the size of the container or amount of the fluid. Then the apparatus is there. Student carried out an experiment to work out the viscosity. This is the same thing we just discussed about how to work out. The density of a glycerol and the ball bearing are known. State two quantities that would have to measure directly to calculate the viscosity. So density of a glycerol and the density of ball bearing is known. What are the other two quantities which we need to do this experiment? Because as I mentioned, if you remember, like we usually plot a graph between V and R square. And how we work out the V? So we measure the distance and time between the markers to get the V, and we measure the size of the sphere by using a micrometer. These are the two quantities which we need. State the quantity that is represented by, so this is volume of object, density of ball bearing, and gravity. And this is volume of object, density of glycerol, and gravity. So like this is a volume of a ball, volume into density is mass. So mass of a ball into gravity, what it does give us? It will give us the weight of the ball bearing. But what about this one? The volume of the ball bearing into density of the glycerol. So volume of object, density of fluid into gravity, what it gives? It gives us the upthrust. So the top quantity is representing the weight and the bottom one is representing the upthrust. Then describe how the results obtained and a graphical method used to determine the viscosity. So how we can determine the viscosity? When you solve that equation which is given above, then the last answer will be the relation between the viscosity and the terminal velocity. So the terminal velocity is 2 by 9. The gravity, the difference in the density of ball bearing minus density of glycerol, R square over eta. Now, this is what we get. Now, if you want to determine the viscosity, so what we'll use a formula y is equals to mx. So first we'll determine the velocity by distance over time, and that we'll plot on y-axis. Then using a micrometer, we determine the radius and then square that, so we'll get a radius square, which is on x-axis. And we repeat the experiment with different size of the ball bearings. We change the size of the ball bearings and we record different terminal velocity and we plot a graph. After plotting a graph, we will find the gradient. The gradient of the graph will be equal to 2. The gravity, the difference in density of ball bearing, density of glycerol over 9 eta. So if we need the viscosity, so viscosity will be 2g, the difference of the density of the two, divided by 9 into gradient. That's how we work out the viscosity. So you have to learn, this is a common repeated question in which you have to work out the viscosity of an object. Then glycerol can be pumped into a waste system to remove the nitrogen during the treatment of a wastewater. Explain the effect of that low temperature would have on the supply of a glycerol. So if the temperature is low, what about the viscosity? The viscosity will be high. So as a result, when it is having a high viscosity, so it will have a slower rate of flow. When it will move slowly through the system, or take longer time to flow. You just have to relate the viscosity. That viscosity, if a temperature decrease, the viscosity increase, which will take much longer time to flow through the wastewater. So this was 29.